not for me to teach any longer. Of course, I can teach until the end of the day, until the end of time about these things. But I think it's pretty much your job now to discover other interesting subjects if you're interested. Because you have the papers you need to present. Oh, by the way, let me just say this: in the next lecture, if you're finished with a take-home exam, you can present your results and you can present your exam next week. I can do that for you. You see what I mean?
Yes. So the paper and
yeah, because you chose the paper, so you need to present the paper. You need to make the simulations in the paper. There is a document on Teams. So there is a document.
Yes, I know, but yes, I know Andrei, because he's not here.
Yes.
Was planning to fix a date during.
Oh, fix. You have to fix that anyway.
Okay.
You can do it also next week. Of course, you can fix a date.
Okay.
Makes
So
sense.
if we can present, and then we don't. We just come to listen the others.
Yes, if you go next, exactly, you come to witness the others. So it's up to you. If you can make it next week, it's fine by me. Okay, but that's not mandatory. Okay. So if you can't make it next week, of course, you can come at the chosen exam date. You see what I mean?
Yes, I will also tell the others.
And these are the papers. If I have a look here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay. And so apparently Theodore chose paper number 8. Florian is still checking. You chose paper number 1. True?
Yes.
Is that right? I mean, we are all looking at this document.
Yes, we use this document for all the.
This is very nice. That's a good idea. That's a good idea for you to use these documents. So, okay, if you're finished by next week, I'm happy to accommodate you and in grading this exam. Okay. If not, like I said, it's not mandatory. If you're not ready by next week, you can come at the exam date you people choose. Okay. But also, please inform me about the exam date. Don't forget to do that. Okay. So once you, yes, go ahead. Please.
I think I can tell you the date, even if, because we have an internal, and for this one, the proposed date is 4th of February at 11 in the morning a.m.
Okay. So
yeah,
please,
but I think Andrei will confirm because he does the paper.
Okay, when Andrei is confirming that, please write it on the channel, on the main channel of this lecture. Write it down.
Okay.
So I do not forget, okay?
Maybe one question about the presentation. How long should the presentation be at the end? Is it
mostly, so tops 40 minutes.
Okay, with the presentation of the simulations included?
Not necessarily.
Okay.
I mean, let's say we should be able to finish in 40, 50 minutes. I don't mind if I'm sitting with a student for 1 hour. I mean, it's up to you, but the main presentation of the theoretical presentation shouldn't be longer than 40 minutes. Let me put it this way. Make sense?
Yes.
So it can be shorter, I don't mind. So I said up to 40 minutes. So if you finish in shorter time and you manage to convince me in 15 or 20 minutes, I don't mind. Okay. maybe I can ask you more questions. Okay.
Okay.
Right. What else? So, like I said, once you pick the date, please write it down on the main channel of this lecture here on Teams, or you can invite me through the calendar, so I can set up a calendar alert. Okay. The only thing is, or write it on the WhatsApp group as well. I don't mind. So anyway, inform me about the date so I don't forget. So essentially, it's the 4th of February. Okay. You said it's the 4th of February at 11 a.m. Right?
Yes,
Yes.
this is what Andrei told us, but I'm not. I don't know what, because he asked other teachers, and I'm not sure what's the status like.
Okay, never mind. I'll just put it here. I don't mind. But that's on a Friday, apparently.
I think so. Yeah, but I
I'm looking
talked
at the
with
calendar.
Andrei, and he will
It's
come to
definitely,
you. To
it's definitely on a Friday.
yes, yes.
Okay, fine.
He will.
I'm fine. I'm fine with it.
Okay, Andrei will confirm today or tomorrow. I told him so.
Yes, yes, yes. No worries. NLC. I'm just writing it. I'm making an event in the calendar just to make sure, and then I'll adjust it. Okay. NLC exam from 11 a.m. Okay. Location, Teams. Okay. So it's done. It's in my calendar. Okay. Just to make sure. Right. Well, any other issues you've got? If you have comments, if you have about the subject, if you are curious about something, please ask me. We can have a free discussion, like a seminar.
Okay.
The subject of nonlinear control. Well, in the meantime, you do the thinking, and then I'll come and discuss, show you what's going on in the lectures of Hassan Khalil. I'm around here, okay? So you've got time to think about it. Oh, Okay. Okie dokie. Okie Okie dokie. Metri, ce dracu să fac, bă, cu el? Așa. Right. Oh gosh. Okay. So, are you people still here?
Yes.
Okay. So,
Yes.
tell me about nonlinear control. Hmm? How did you find the subject?
Difficult.
Oh, hi, Theodore. Haven't seen you. Welcome.
Yeah, sorry,
So, yeah, this
I've
is
just
a
joined.
discussion about nonlinear. Yes, it's a difficult subject, I admit, very difficult. It's at least master level. But I try to show you the basics of this. Nonlinear control involves a lot of mathematical knowledge, calculus, multivariable calculus, differential equations, calculus of differential equations, and a lot of things. And differential geometry, nonlinear control, as you saw last week, it's all about differential geometry with the Lie brackets and the Lie derivatives and other things. Okay, it's the geometry of the trajectories. And the idea is that when you do control, you try to adjust the trajectories to a specific behavior you desire. Okay. And there's many notions involved. Stability is the main issue, and as you have seen, stability is not about the stability is not about the entire nonlinear systems, but it's the stability of a specific simple trajectory called the equilibrium point. Okay, the stationary point. That's it. If the stationary point is manages to attract all the trajectories in a neighborhood, then it's a stable equilibrium point. Okay, and we saw all sorts of characterizations mainly the main ingredient being the Lyapunov theory. Okay. Another interesting ingredient is passivity. What is passivity? Essentially, passivity is a physical property saying that a dynamical system is not accumulating energy when it is subject to an energy input from the exterior, from external sources. Okay, that's mainly passivity, and passivity is since it's an energetic notion, is very much related to stability. And we touched this subject a little bit when we discussed Lyapunov stability. Now, passivity and input-output stability, as we see in this lecture of Khalil, it will be related. Okay. Memoryless functions, that's what it says here. For instance, this is the first one is a passive, A is a passive function, B is a passive function. Okay, because why? Because we see a specific shape of the trajectory before before the time, you see. Whereas in the C, in the C part, we can see another type of trajectory. It's related to this notion of memoryless functions. Okay, the power inflow you get for a system which is fx and u and y is hx, that's the output, is the product. Power is the product between the input transposed and the output. Okay, these two vectors. Okay, if when it's scalar, it's just the main function product u times y. Okay, so essentially passivity is related, as we can probably gather through intuition, is based on the choice of inputs and outputs. Okay, on inputs and outputs. You see? Okay, so an output, actually, you can call an output h depending on time t, and on the input you give it u, is passive if the product u transpose y is non-negative and lossless. We can have that lossless. So it's lossy if u transpose y is positive, and lossless if u transpose y is 0. And we also have additional or particular instances of passivity, such as input passivity. Okay, when u transpose y is larger than u transpose in another function of u for some function phi, satisfying this positivity property. And output strictly passive if on the output we have this a specific property, such as the power flow u transpose y is lower bounded by this function depending on the output. Okay, and here we discussed about nonlinearities. If you remember, they present, for instance, the sector type nonlinearity, which we discussed when we were talking about absolute stability. And the memoryless function, it says here, is said to belong to a sector, and there are a lot of conditions satisfied if these conditions are satisfied. Okay, right. And here there is a discussion about how to put all these ingredients at work for passivity. And now, what is a passive state space model? Okay, what is a passive dynamical system essentially? So if you have the dynamical system x dot is fx and u and y is hx and u, is passive if there is a continuously differentiable positive semi-definite function v. You remember that this is also apparently is also related to a Lyapunov candidate function, but in general v is called a storage function, such that the product u transpose y is lower bounded by v dot, the Lie derivative of v. If you remember this, we discussed, we have this notion since Lyapunov stability. If you look here, okay, you know what v dot is when we discuss Lyapunov stability. Lossless if u transpose y is v dot, input strictly passive, output strictly passive, and strictly passive if U transpose Y essentially is strictly larger than V dot, or is U transpose Y is larger than or equal to V dot plus some function of the state, some positive function of the state psi, okay? And here's an example. Here's a simple example, yeah? We have this integrator, yeah? X dot equal U, that's an integrator system because X is the integral of U, okay? So this is an integrator. This is a linear system, so if you apply the Laplace transform, you get the transfer function between the input U and the output Y is 1 over S, okay? But let's analyze this from a dynamical point of view. So selecting the storage function Vx is half x squared. This is an energy function, true. Then U transpose Y is U, is actually V dot, because it is X, yes? Uy is X, so it's V dot, right? No, it's sorry, it's X times U, that's V dot, yeah? Because V dot is what? Is twice X dot. No, sorry, 2 times half, that's 1. So that's X dot, and X dot is U. So indeed, Uy is V dot. So this is a lossless, the integrator is a lossless system. It doesn't lose energy. So the energy of an integrator, once you plug it into some energy source, is not decreasing, is not increasing, but remains constant. Remains constant. Okay. Now, if you take another output, you see, you take a different output. You take the output X to be the output Y, sorry, to be X plus some function depending strictly on, or only on U. Okay, H is a non-negative function. Then indeed, this is a passive system because U transpose Y is strictly larger than V dot. Okay, and all sorts of things, Input strictly passive. Also, if you pick X dot to be any function H positive of X with a minus sign plus U, if you do Uy, you realize, or you find out that this system is indeed passive and output strictly passive. Okay. The storage function V is not unique. Is not unique. Just like in the Lyapunov stability case, the Lyapunov candidate functions, they are not unique. We know that. Okay. So if you pick another storage function, Vx is integral from 0 to x of any function h. Okay. Then V dot is hx times x dot. Okay. Makes sense. And that's yu. This is again a lossless system. Again, a lossless system. Now let's take taking the particular case of a linear scalar system. Ax dot is minus x plus u, is a non-zero. Okay, and if you take the storage function Vx to be a times integral from 0 to x in the h, then we can compute that if we pick, if we do the power product U times Y, we get that the system is passive, and if H is non-zero function, is strictly positive, then actually the system is strictly passive. And you see, we have all sorts of variants here, depending on the type of system. These are simple examples, but this passivity property, this is widely used passivity property, and actually also in the linear systems case, we talk about positive real functions. This is the linear version of passive systems. Okay, and they are quite important also for control. Okay. Yeah, so it says here positive real transfer function, a rational function, a square rational function matrix. Okay, GS is positive real if the poles of the elements of all elements of GS are in the closed left half plane, and furthermore, for all real numbers omega, for which j omega is not a pole of any function of GS. Okay, GS is again is a matrix of rational complex functions, complex rational functions. Then positive realness means that G of j omega plus G transpose of minus j omega is positive semi-definite. Okay, and any pure imaginary pole j omega of any element of G is a simple pole, and the residue matrix is positive semi-definite Hermitian. You know what a Hermitian matrix is? A Hermitian, this is for complex matrices. A complex matrix is Hermitian if A equals A transposed and conjugated. Okay, right. So this is a positive real function. Okay, then we take the scalar case, m equal to 1. Then g of omega, this is a transfer function. This is a function, a complex rational function. G of j omega plus G transpose of minus j omega is actually twice the real part of G of j omega. This is we know that the real part of a transfer function in j omega, evaluated in j omega, is an even function, and the imaginary is an odd function. Okay. Hence, a transfer function is positive real if for a j omega, the real part of G of j omega is non-negative for all the frequencies omega between 0 to infinity. Okay, meaning that the Nyquist plot, if you remember what a Nyquist plot is, of G of j omega is in the closed right half plane. Okay, right half plane. Okay, now also they say here this is true, and now it's related to some notion we have been discussing recently. If the relative degree of the transfer function is 0 or 1, relative degree, you remember, is the pole 0 excess of a transfer function. So the difference between the degree of the nominator and the degree, the degree of the denominator and the degree of the nominator. And if the system is proper, okay, degrees are equal, excess is 0, relative degree is 0, or 1, that means there is one additional pole than a 0, then this condition is true. And now we have a lemma characterizing the property of positive realness of transfer function matrices. GS is Hurwitz polynomials with the roots, with all the roots in the open left complex left half plane. G of j omega plus G transpose minus j omega is positive for all omega, and also at infinity is positive, or this limit is positive where this number q is the rank of this matrix. Okay, and in the scalar case things are a bit easier. And we have a very interesting result for linear system, a crucial result. This is the so-called positive real lemma. This is a crucial result in control. Considering a a linear system with a transfer function C is Si minus A inverse B plus Z, where the pair AB is controllable and the pair AC is observable. Okay. These two conditions for state space system, which probably you need to recall. GS is positive real if there exists a matrix or matrices P positive definite L and W such that this system of three matrix equations has a solution. Yeah, the first one, if you look closely, the first one is a Lyapunov equation. The second one, well, anyway, is just a matrix equation, and the third one as well. So this is the characterization. This is the positive real lemma, crucial result, okay, for passivity. And another crucial result is the so-called Kalman-Yakubovich-Popov lemma, okay, also crucial result, okay. So G is strictly positive real if and only if there exist matrices P, positive definite, and matrix L and W, and the positive constant such that this system has a solution, okay. Okay, right. So they're asking here, this result says when a linear time invariant minimal realization is passive, okay, and the connection of passivity with stability. We have the connection of passivity with stability. Considering a nonlinear system, x dot is fxu with the output h, y is hx and u, is passive with a positive definite storage function v. So if this is passive with a positive definite storage function v, then the origin of the system is stable. This looks like Lyapunov stability, doesn't it? It's about the energy. Okay. So Lyapunov stability is actually relying somewhat on this notion of passivity. Okay. Yep. And there is a proof here, okay, anyway. Furthermore, if the system is strictly passive, then the origin is asymptotically stable. Okay? And if the storage function is radially unbounded, this is a nonlinear property, then the origin is actually globally asymptotically stable, which is a very powerful result. Okay? And now we need to characterize when a system is to do a simpler characterization, not because we don't want to check the passivity inequality all the time, because this can be very difficult most of the times. So we need to rely on some other properties of the system we can easily check. So the system x dot is fxu, y hxu is zero state observable if no solution of x dot is fx can stay identical in this set other than the zero solution. Okay. So the idea is that if the output is zero for no input, okay, if only the zero solution, if only zero is the solution, okay, of the system, okay, when h is set to zero, then the system is called zero state observable. Okay. The particular case of linear systems, if you have the linear system x dot is ax and y is cx, the zero state observability is equivalent to the observability property of the pair of the matrix pair CA or AC. Okay. Essentially, if y is 0, then x of 0 is 0, in the equivalently x of t is 0. So it's equivalent to observability. Okay, observability. Well, if the system is output strictly passive and zero state observable, then the origin is asymptotically stable. Okay, and here is a proof. Okay, so strictly passive characterized like in the first member of the equation. Then when you set u to 0, you get this inequality dv dx fx, that's v dot, is strictly is upper bounded by minus y transpose and the function of y. Okay, then if v dot x is 0, you get y equal to 0, and then x is equal to 0. Okay, and the invariance principle and so on, the invariance principle of Lasalle. Okay, and then you get stability. And here is an example of this. Here's an example of this. We have this nonlinear system. Okay, and you pick the storage function 1 over 4a x1 to the 4th power, and since x2 only appears linearly, you apply you take if you consider x2 speed, the velocity, essentially 1 over 2 x2 squared is the kinetic energy, and 1 over 4a x1 to the power 4 is actually the potential energy. And v dot, you compute v dot, is not very difficult to compute, okay, is minus ky squared plus yu. The system is output strictly passive, okay, y is 0, and then you follow all these equalities, and actually the system is also 0 state observable. Okay, so the origin is an asymptotically stable point. Okay. Well, L stability. Okay, it's about stability of the systems in terms of L infinity or L2 stability. Okay, for instance, LP spaces, we know the infinity norm and the 2 norm and the P norm in general. Okay, so we have a lot of, you see here, a lot of difficult notions and characterizations of stability in terms of norms. We don't get into these details because they're not so easy. Okay. Then, based on this passivity, I want to look at passivity-based control and see if I get here some or any insight into this. Oh, stability of feedback system. This is also quite important. So this is how you pose the stabilization problem in control perspective, and how you use passivity. So the feedback interconnection of two passive systems is passive. This is a crucial result. Yes. So if H1 and H2 is passive and you interconnect them in this framework, the resulting connection is passive. This is a great result. This is a great result. And this is crucial for control design. This is very good for control design, okay? We don't get into the proof here, but the proof is not very difficult if you look. It's not very difficult. Asymptotic stability, consider, so we have now a great result linking the asymptotic stability of the equilibrium of the origin of a feedback interconnection of two passive systems, or feedback interconnection and passivity. So consider the feedback interconnection of two dynamical systems. When u equals to 0, the origin of the closed loop system is asymptotically stable if one of the following conditions is satisfied. Both feedback components are strictly passive. Okay. Both feedback components are output strictly passive and 0 state observable. One component is strictly passive and the output is output strictly passive and 0 state observable. So this is great. You see, so actually these three conditions provide us three strategies for control design, for stabilizing control design. Very nice. You see, so this nonlinear world is offering is offering a lot of options. Of course, you have to understand that the more options you get, the more complicated the theory is. We can't help it. This is not easy. Nonlinear control design is not something you can do in a couple of minutes, just applying some results. These are the basic principles, but to essentially get a quantitative version, specifically to get a concrete controller, the way is very long and very tedious. Okay. And here are some examples. For instance, if you interconnect these two systems, very interesting example. You pick V1 and V2. H1 is output strictly passive and zero state observable. Okay. And H2 is output strictly and zero state observable. Then the origin of the interconnection is globally asymptotically stable. Bingo. You hit the jackpot. Of course, like I said, these are very easy examples. To apply this on general nonlinear systems, things are not so easy. That's why you have all sorts of variants of nonlinear control design. Okay, and other interesting results. Okay, other interesting results. You can see here. For control design, okay. Small gain theorem, another very crucial result. So now, if you look at stability from the perspective of low errors of output and input signals, okay, L2 norm or L infinity norm, you have the so-called small gain theorem, okay. Small gain theorem. The feedback interconnect, so if you have these two systems and you satisfy these conditions of LM stability, then the feedback connection is finite gain L stable if the product gamma 1, gamma 2, where gamma 1 and gamma 2 are actually the bounds on the outputs of the L norm of the systems, okay, then the interconnection is stable in the sense of a finite L norm gain if the product gamma 1, gamma 2 is less than 1. And the small gain theorem, even also for linear system, is opening a wide field, a wide range of, again, of control, difficult control strategies, but very effective. Difficult, but very effective. Another case is the absolute stability, which we discussed. We discussed absolute stability based on the KYP lemma, if you remember, with the S procedure and the sectors and all of these things. You can look at it. You have here the circle criterion, okay? And you also have the Popov criterion. This is the circle criterion. You also have the Popov criterion, okay? You recognize here -1 over beta, Popov criterion, you remember that. Okay, so things are interconnected. Theory is very clear. Okay. And you remember the Popov plot and the fact that this new Nyquist plot, this adjusted Nyquist-like plot, needs to lie on the right-hand plane denoted by the Popov line. You see, you have here an example. Yeah, okay, very interesting. So what else do we have here? Special nonlinear forms. Okay, we do not get into this. What else? Lecture 9, state feedback stabilization concepts. Okay, here they defined very nicely the steady state problem. What is a steady state in nonlinear setting? And you have here notion of stabilization. Okay, local stabilization, regional stabilization, global stabilization, semi-global stabilization, all sorts of things. Very, very, very interesting. Very interesting. Okay. You can have a look anytime you like, and you can learn control from these lectures like you have never learned before. Okay, robustness, observers, okay, state observers, output feedback stabilization. Okay, tracking and regulation. So here we discussed this, if you remember, when we did feedback linearization. Yeah, very interesting. Another way of looking at things, and you can look at these things yourselves. Okay, Khalil, the page of Khalil, very, very nice, very nice. Okay, very nice. Here is the extended version, so you have a lot of details in this. A lot of details. You can see it here. Lectures and lectures and lectures. Very nice. Yes. Everything explained very clearly. So this can be very useful if you encounter some of these issues in your in your studies. Okay. Very interesting. It's a huge subject, and there's a lot of books. Yeah, passivity. So we just discussed that. Input output stability. Yes. I also found, interestingly enough, I know this guy, Arjan van der Saft from Groningen. He was the PhD supervisor of my PhD supervisor. Very smart guy. And he's very good in this nonlinear control things, also geometrical nonlinear control with Dirac structures and port Hamiltonian systems. And here in the lectures, they are teaching a lot of courses in the Netherlands, also for at graduate level. And here we have stabilization and passivity-based control. This is the lecture taken from another famous guy in nonlinear control, Rodolphe Sepulcre. I think he's Belgian. He used to be in University of Liège, but now he's in Imperial College for the last years. Okay, and these are slides about stability and passivity-based control, which is another important technique of nonlinear control. Okay, so here it's explaining what a stable equilibrium point is, Lyapunov theory, which we are familiar with because we studied this in detail. You have a control system, okay, right? So the problem of stabilizing state feedback, finding an input u equal alpha x such that the closed loop system has an asymptotically stable equilibrium. Okay, and this is how it looks for the linearized system. The linearized system, you know how to linearize, is this one, x dot is ax plus b u. You have the controllable subspace of the linearized system, okay? if the system is not controllable, you can always apply a controllable decomposition, a controller decomposition, where now if the pair AB was not controllable, the pair A11 B1 is controllable, and the pair A22 0 is not controllable. Okay, and essentially you can only do stabilization on the controllable part of a system. So if you pick U equal Fx, okay, and you split Fx in F1 and F2 on a line, and if you apply A plus Bf, because U equal Fx in substituted in the equation x dot is Ax plus Bu, means that x dot is A plus Bfx. Well, when you split A plus Bf, you notice that A11 plus B1 F1 can be modified through F1, whereas A22 is fixed. So the uncontrollable part is always fixed. You can never change the uncontrollable part. So that's why control is only useful, state feedback control is only useful on the controllable part of the system. Okay. Well, when is a system, however, an uncontrollable system stabilizable, actually? When can you stabilize an uncontrollable system? Well, stability of a linear system means eigenvalues in the open left half plane. Well, you can change the spectrum of A11 through F1. A11 plus B1 F1 can have the spectrum located forcefully in the open left half plane. But what happens to A22? Well, A22 is uncontrollable. A22 has a fixed spectrum. Hence, if you want the entire system to be able to be stable in closed loop, you would like A22 to be already stable. So a system AB is stabilizable if and only if the uncontrollable part is already stable. Okay. It says here, moreover, if one of the eigenvalues of A22 has a positive real part, then there doesn't exist a solution to the local feedback stabilization problem. Okay. And here there are some explanation about this. Okay. You have the linear dynamics, and you assume all the eigenvalues of the controllable part, the uncontrollable part, are stable. Then there exists a state feedback, a linear state feedback, to asymptotically stabilize the linearized system, essentially in A11 B1 in the controllable part. Okay, and then you apply, for instance, this local linear feedback to the nonlinear system, and in closed loop, when you linearize, you get A plus Bfx. By construction, this linear dynamics is asymptotically stable. So, through Lyapunov's first method, x0 is an asymptotically stable of the nonlinear system. So you can also do this. You linearize, you do state feedback, and locally, but this is only very local. Okay, this is only very local. You can stabilize. Okay. So, well, what happens if the uncontrollable part has at least, for instance, a positive real part? Okay. So you cannot do anything about it. Okay. Another idea to look at things and to do stabilization is looking at the so-called center manifold theory and theorem. This is a crucial result in nonlinear theory. Okay. The idea is that you can write the spectrum of a matrix as the disjoint union of the stable and the unstable eigenvalues. Okay, and you can count them, and then you can also have a coordinate transformation such that you can write your matrix in this block diagonal form, where one block contains the stable eigenvalues, and the other block contains the unstable eigenvalues. Okay, so you can also do that. Well, center manifold theorem. So for each k, who is k? I'm missing this. Who is k? There exists a delta k and a ck mapping phi defined as z1. Okay. Such that the submanifold, the center manifold Z2 is phi Z1, is invariant under the nonlinear dynamics. Okay. Well, you see, and this is in closed loop. This is in closed loop. The closed loop matrix. Okay. Right, and then you have the Lyapunov method here. Yeah, which we know already. And there is an example of the angular velocity of a rigid body with an external torque. Very interesting. Passive systems, okay? So, again, a system is called passive if you have a storage function, non-negative, if and the system is passive if and only if S dot is less than y transposed u. Okay. In physical situation, it says here S is often the stored energy. Okay. You have the available storage and the required supply. These are two important storage functions. Okay. Well, LFX is negative definite H with HX G transpose DAS DX. Okay. So passivity can be regarded as an extension of the notion of Lyapunov functions, the storage function. I said we know that. Okay. So passivity-based control, essentially, you would like to take a feedback, okay, to satisfy this this equality to lead to the passivity inequality. Okay. Okay. In general, a passive system has uniform relative degree 1. Very interesting. Yeah, you can prove that. Okay. You can do backstep. We didn't discuss backstepping. This is another discussion. Okay. And you also can do passivity-based control for system in a geometrical fashion. Okay, we do not get into these details where you look at flows and efforts, and you can do port Hamiltonian systems and Dirac structures and all these very complicated things. Okay. Well, like I said, there is a lot of information about nonlinear control. I try to give you the basic things of these notions, and to ask you to solve some assignments, which I'm expecting you to have ready by next week. So next week, the assignments will close, and you get points for the assignments you have managed to solve, to sort out. And then you have to do the take-home exam to present your paper and show me the simulations and show me how you did research on the paper and what's your take on the results in those papers, and so on and so forth. For me, that's all I had to say in this lecture. I think there is a lot of information, and honestly, I hope you enjoyed it. So if you have any questions and comments, please now is the time. I'm listening.